Hello students, welcome back to this channel. In this part, we are going to learn about measuring long distances. For example, how to measure the distance between the Earth and the Moon, or the distance between the Earth and the nearest star. You know several measuring instruments, but we do not have measuring instruments to measure such a long distances. So we need to look for some other techniques to measure long distances. There are some special methods like radio echo method, laser pulse method and parallax method. Let us start with the radio echo method. In this method, we take the nearest star X as our target. Our aim is to measure the distance between the Earth and the star X. Radio echo method uses sound waves to measure the distance between the Earth and the star. You can see the sound source here, that is from Earth. So the sound waves will be transmitted from Earth towards the star X, and the time taken by the sound waves to hit the target and come back will be measured. The red and green lines indicate the directions forward and backward. So to and fro distance should be measured. Now we measured the time. So how to get the distance value? You know the relation between the distance and time, speed equal to 2 times distance by time. So the speed and time are here known quantities. You can calculate the distance. The speed of the sound wave in air is 340 meter per second. So substitute the speed value and time value, so we can get the distance between the earth and the star. Next, we move on to laser pulse method. Laser pulse method uses electromagnetic waves to measure the distance between the Earth and the star. The same procedure is used here. The only difference is laser light has been used instead of sound waves. The next is very interesting method, parallax method. First, we must learn what is parallax. Parallax is defined as the apparent change in location of an object seen from two different places. Let's see with an example, then you can understand well. Take any one object and focus it with your left eye. You just keep your thumb like this and close your right eye. Observe the position of the object. Do the same with your left eye closed. You can feel the apparent displacement of the object. This is called parallax. Let's check with another example. Look at this picture. Here you change your viewpoint side to side. Focus on the white cube which sits in front. It appears to move faster than the green cube at the back. This is called parallax. So nearby objects show a larger parallax than further objects when observed from different positions. So parallax can be used to determine the distances. So in this slide, we are going to measure the distance between the nearest star and Earth. Look at this picture. This is nearby star and these are stars at longer distances from Earth, that is background stars. The nearby stars appear to move faster with respect to the background star due to the motion of the Earth around the Sun. In this picture, we have 2 points, one at December, other one at June. Here the line of sight to the star in December is different than that in June, since the Earth moves to the other side of the orbit in June. Thus the nearby star appears to sweep through some angle, and this is intersection of line of sights. Half of this angle is called the parallax angle. So the distance to the star can be calculated using the formula d equal to 1 by p. Thus we measured the distance between the star and the earth using the parallax method. So next we are going to learn about astronomical unit. Astronomical unit and the light year are used to measure distances within our solar system. Astronomical unit is defined as the mean distance between the center of the Sun and the center of the Earth. One astronomical unit equal to 150 million kilometer or 93 million miles. As well, the light year is defined as the distance traveled by light in 1 year in vacuum. The distance traveled by light in 1 year is given by velocity of light times 1 year in seconds. So, if you substitute the velocity of light value and 1 year in seconds, we will get 9.467 times 10 raised to 15 or 9.5 trillion kilometers. So, one light year equal to 9.5 trillion kilometers. Thanks for watching.